Hmm.
We're going to explore how many 7 by 7 squares can fit inside an 8 by 8 grid. This is a fascinating problem in combinatorial geometry that demonstrates systematic counting principles. Starting from the top left corner, we can place our first 7 by 7 square. This square occupies 49 of the smaller grid squares, leaving one column on the right and one row at the bottom unused. The second 7 by 7 square starts from the second column in the top row. Notice how it overlaps with the first square but creates a distinct positioning that allows it to fit within our 8 by 8 grid. The third 7 by 7 square begins from the second row in the leftmost column. This creates another unique position where a complete 7 by 7 square can fit within our grid boundaries. Finally, the fourth 7 by 7 square starts from the second row and second column, occupying the bottom right area of our grid. This is the last possible position where a complete 7 by 7 square can fit. We can calculate this result using the formula n minus k plus 1 all squared, where n is the grid size of 8 and k is the square size of 7. This gives us 8 minus 7 plus 1 squared, which equals 2 squared, which equals 4. In summary, we can fit exactly 4 7 by 7 squares within our 8 by 8 grid. Each square occupies a different starting position, but they all overlap within the same grid space. These 4 squares represent all possible ways to place a 7 by 7 square within an 8 by 8 grid. This visual demonstration shows how systematic positioning allows us to find all possible placements of larger squares within a grid structure. Now, let's understand the mathematics behind why there are exactly 4 7 by 7 squares that can fit in an 8 by 8 grid. A 7 by 7 square needs 7 consecutive cells in both horizontal and vertical directions. The key insight is understanding where we can place the top left corner of this square. Since our grid is 8 by 8, the top corner can only be placed in positions 1 or 2 horizontally and positions 1 or 2 vertically. This gives us exactly 2 times 2 equals 4 possible positions. This follows a general pattern. For any n by n square in an 8 by 8 grid, we can place it in 9 minus n, all squared, different positions. Let's apply this formula to count all possible squares in our 8 by 8 grid, starting from 1 by 1 squares up to the single 8 by 8 square. Now let's add up all these counts to find the total number of squares in our 8 by 8 grid. So our 8 by 8 checkerboard contains exactly 204 squares of all different sizes. The 4 7 by 7 squares we found earlier are just one part of this complete pattern. This mathematical approach shows us that counting squares systematically using the formula gives us a complete understanding of all the squares hidden within our grid.
Why would you not subscribe?